Yeah, you can start.
Okay. Good morning to everybody in India, and a good evening to those of you joining from the United States. Welcome all of you to the thesis defense of Siddharth Bhandari. Siddharth will be presenting the results of his research work done over the last few years. A quick introduction to Siddharth and his work. As an advisor, one is faced with the task of finding the right problem for the student to work on. This is, of course, a classic conundrum for anyone in research. What is a problem that is both challenging on one hand as well as solvable? In this case, within the stipulated PhD period, in TIFR, the 5-year period, this is where the advisor comes in and supposedly provides their sagacious advice and wisdom. I don't know how true this is in my case, but a large part of my interaction with my graduate students has been spent on finding a problem in a research area, some area where I'm competent enough to advise them, as well as something that is challenging and worth the student's effort. This journey has been and continues to be one of the most enjoyable experiences with all my students so far: Girish, Swagato, Rakesh, Siddharth, Tulasi, Argo, and Aparna. In Siddharth's case, this problem was further compounded because he would flit like a bee from problem to problem, research area to area. A large part of my concern in Siddharth's early PhD years was to find a problem that could hold his interest. To make matters worse, not only would he hover from area to area, he would take me along on this roller coaster ride. We have spent innumerable hours discussing various topics under the sun. To Siddharth's credit, he did manage to convert some of these meandering explorations into successful enterprises. His first success was related to the zero-error list decoding problem, a problem introduced to him and me by Jayakumar. Then, intrigued by Piyush's Markov chain course, he successfully and perfectly sampled a few problems in joint work with Shayantan and Piyush. Both these areas were novel to me, and I learned a lot in this process. He then honed in on algebraic coding theory, a topic close to my heart, where we, in joint work with Mrinal, Kumar from IIT Bombay, Madhusudan, Harvard, and Aparna, a fellow student at TIFR, proved a few results. As part of his thesis defense presentation, Siddharth will be presenting a sub-collection of the results he proved during this roller coaster ride. Just a couple of things about the thesis defense. The committee will comprise of Professor Venkatesan Guruswamy, who is joining from CMU Pittsburgh. Thanks, Venkat, for joining in this late in the day. Professor Jayakumar Radhakrishnan will be the subject board representative, and myself, Siddharth's advisor. The thesis defense will consist of two parts: a public part, which is open to everyone, and then there will be a closed door, or as closed door as it can be on Zoom, the end of this one, at the end of the day. Okay, let's, without any ado, get started. Siddharth.
Thanks, Prahlad, for that introduction. And as you can see in the title slide, this is the roller coaster that Prahlad was talking about. And firstly, thanks everyone for being awake at this early hour in the morning. Luckily, it's not early for me here. And thanks, Venkat, for being awake at this late hour. Okay, before I get on with the presentation, I would like to say a big thank you to everyone at TIFR for these 5 years. It's been a wonderful journey with its ups and downs and curves and flats. And it kind of feels surreal trying to encapsulate it in a blink. But I guess that's what life is. Anyways, moving ahead, this talk is going to comprise of 4 results. And they are going to be about exact sampling and list decoding, as the title says. So let's move ahead. Oh, I can't change my slides first. Yeah. So feel free to stop me at any point if I am not clear. And hopefully you will get something out of the talk. So the first result I'll talk about will be about colorings. And the outline will be that I'll just try to present the result and the context of the result. And hopefully when we will have time towards the end, I'll try to go into the proof technique of one of the results. So let's begin with the result on sampling colorings. So this was joint work with my colleague Shayantan, and we received lots of help from Jayakumar, Piyush, and Prahlad. Was there a question? Okay, so let me move ahead. So let me introduce the problem statement. So we are given a graph G on n vertices and of maximum degree delta, and a set of prescribed colors. Here I denote them by the set square bracket k, which is just, you can think of them as numbers from 1 to 3 up to k. And we are interested in the set of proper colorings of this graph, which I'm denoting by script C. So by a proper coloring here, I mean a vertex proper coloring. So you have to assign a color to each vertex such that no two neighboring vertices receive the same color. And what we'll be interested in is the uniform distribution over this set, which we are going to denote by capital pi. Okay? So the distribution which puts equal weight on every coloring which is proper. And what is our task? Our task is to sample efficiently and exactly according to pi. In other words, I want an efficient algorithm which runs in time polynomial in the input size, the graph, and the set of colors. And it, in the end, terminates with a sample which is distributed exactly as pi. So I don't want to be close to pi. I want the distribution to be exactly pi. So there is emphasis on the word exactly. Now, of course, it is well known that trying to determine whether this set is empty or non-empty itself is a hard problem. So to have any hope of sampling over such a set, we assume that k is at least larger than delta plus 1, because this is like the greedy threshold. Here we know that a coloring will exist by just a greedy algorithm. And in fact, we'll assume that k is a constant times delta, with the constant being greater than 1. Another thing I would like to bring to notice is that a naive accept reject algorithm, which just tosses a color, a random color for each vertex and hopes that the coloring is proper, will not work, as typically this ratio will be exponentially small in n, so it would take forever. So what is the goal in such a kind of work, or in such algorithms? The goal is to keep the value of c as small as possible while still being able to efficiently sample from pi. So that is the sort of game we are after, and of course it's the holy grail to get it to delta plus 2. But right now, even getting it to some constant times delta for c greater than 1 will be very nice. So I would like to highlight a previous work of Huber in 98, where he showed a very nice algorithm. In fact, it was seminal for various reasons, where he shows how you can exactly sample from pi if the number of colors that you are provided is actually quadratic in delta. So it's not exactly a constant times delta, but a quadratic in delta. In particular, it was delta square plus 2 delta. And our result, essentially, that is my work with Shantan, it brings this quadratic threshold down to a linear threshold, in particular down to 3 delta. So as long as the number of colors prescribed is 3 times more than the degree, we give an efficient algorithm to exactly sample according to pi. So I hope the problem statement and results is clear to everyone. So moving on, I would like to introduce the method of choice for almost all sampling algorithms for colorings, which is the Markov chain called Glauber dynamics. It's a very simple Markov chain, with the state space being the space of all proper colorings, script C, and the stationary distribution being the distribution we were interested in, pi. And how does one step of this Markov chain work? So it takes a coloring chi, and it chooses a random vertex in the graph V, and then it chooses a random available color at V. So what do I mean by available? So if you look at the vertex V, the colors blue and red are blocked because they appear on the neighbors of V. So we choose a color which is available. So in this case, let's say we choose a color C randomly from the set of available colors, and it happens to be yellow. Then we just update the vertex V to have the color yellow. So it's as simple as it can get. And this Markov chain forms the basis of almost all sampling algorithms. So first, I will talk about a different paradigm to better contrast our results. So this is the paradigm of approximate sampling of colorings. Here, the demand is weaker. Earlier, we wanted to terminate with a sample which was exactly distributed as pi. Here, we are sort of happy terminating with a sample which is distributed according to some distribution close enough to pi. So in particular, this closeness can be measured in terms of the total variation distance. And we can have an error parameter epsilon, and we want the total variation distance between our output distribution and pi to be less than epsilon. And the algorithms in this regime typically proceed by taking a coloring x0, a fixed coloring x0, which one can find using a greedy coloring at the values of k one usually works with, and then just keep on applying the Glauber dynamic updates a fixed number of times, t times, let's say, and output the random coloring xt at the end of it. And one usually shows that when t is set large enough, this distance between xt and pi is sufficiently small using a coupling argument or some spectral methods. But generally, the value of t scales as log of 1 over epsilon, where epsilon is the error parameter. However, such a setting is infeasible for our tasks because we want epsilon to be 0. We want no error in our sample. So this would take forever. Hence, we need to do something different. Now one can ask, okay, if we can sample approximately so well, like we can get to within epsilon in log 1 over epsilon steps, then why do we bother with exact sampling? Well, the first thing is I find it very elegant and interesting, and some of the work that has come out trying to address these problems constitute one of the prettiest algorithms I have seen in in field of probability and randomized algorithms. And they also help in another theoretical construct that of being counting algorithms. So there is a theorem of Huber which shows that if you use a perfect sampling algorithm for designing an FP RAS, it tends to have better performance than using approximate sampling algorithms. And the more important thing I think is that they have a stopping criteria which comes inbuilt generally. So unlike approximate sampling algorithms where you have to run for a fixed amount of time step and then somehow rely on some theoretical analysis saying that it mixes fast, exact sampling algorithms typically tell you when to stop. What the theoretical analysis tells you is how long it will take to stop. So for instance, you can get a problem from nature where actually the Markov chain does really well, but you would never be able to enjoy its advantage if you use the approximate sampling algorithms because you would have to run for the predetermined number of steps or use some heuristics otherwise. But exact sampling enjoys the benefit that if the Markov chain really does mix fast there, you would know, like the algorithm will terminate quickly. That being said, now let's see the contrast between the results known for approximate and exact sampling. So the seminal result in approximate sampling started with Jerem's work, where he showed that the Glauber dynamics mixes fast whenever the number of colors is at least 2 times the maximum degree. Boublil and Dyer reinterpreted this result in terms of path coupling, which has been very influential from there on, because it provides a very nice way to argue for coupling contraction. And then there was a huge line of work and lots of results for special families of graphs. But for general graphs, the next big breakthrough came from Vigoda's work on flip dynamics, which essentially also shows that the Glauber dynamics mixes fast even when the number of colors is like 11 by 6 delta, so slightly below 2 delta. And very recently, Chen, Delcourt, Moitra, Perano, and Postal improved the 11 by 6 by another tiny constant. So you can see it's kind of like an arms race here. And it's really important to try to drop this constant down. On the other hand, if you look at exact sampling, the results known were much more modest. So it starts with Huber's work, where, as we discussed, he shows a quadratic bound, the k being greater than delta square plus 2 delta. And then recently, Feng, Gu, and Yin actually obtained an improvement on Huber's bound, however, in the linear terms. So it's still quadratic and for restricted family of graphs. So where the number of colors is log the number of vertices. In other words, the degree doesn't grow too quickly as the number of vertices grow. And in another remarkable work around the same time, Liu, Sinclair, and Srivastava actually designed a deterministic approximate counting scheme for bounded degree graphs, which matches Jerem's threshold. However, this scheme is efficient only when the graph has bounded degree. So for general degree graphs, the best thing that was known was still the quadratic barrier that Huber produced. And essentially, our work breaks this quadratic barrier and we get a linear bound instead. We get an algorithm which works even when the number of colors is around 3 delta. And subsequent to our work, this was actually further improved in a beautiful work by James, Shah, and Sony using the constructive Lovász local lemma, where this 3 gets replaced by 2.66 essentially. So that's all for the result on colorings. If we have more time, we'll come back to this. Now I would like to change gears and talk about a different result, which relates to the zero error capacity of a particular channel. And this, in fact, chronologically was the first result of the 4 that I got. This was joint work with Kumar, and we received lots of help from Prahlad and Ramprasad. So let's dive into it. So what is the zero error capacity of a channel? So it's a very fundamental notion of transmitting information where the recovery happens perfectly. So imagine, you have a noisy typewriter channel, which is a classic channel. It's a channel where if you type something, let's say you type I, then you can get any output, which is either I or J. So either the letter you input or the one after it. And you want to understand that under such a model of noise, which is adversarial, so anything can happen, is it possible to recover some meaningful information? And this can be modeled in terms of the confusability graph of the channel, although I won't go deep into what that means, but these are well-studied notions in information theory. And as it turns out that although this problem has received considerable attention, I mean, in general, the area of zero error information theory, making progress on problems here is typically very difficult, and the combinatorial challenges that come up lead to beautiful techniques. A landmark result here is Lovash's result, where he determines the zero error capacity of the C5 graph, and it led to the introduction of semi-definite programming. So the star of our show, however, will be a cousin of the kind of channel we just looked at. It's a channel which behaves in this perverse manner. So the input alphabet is the set of symbols 1, 2, 3 up to Q, which I'm denoting by square brackets Q, and the output alphabet is the same. If you input a symbol I, you are guaranteed to get something which is not I. So it can be any other symbol but I. And of course, this noise is again adversarial. So when you take a symbol, the adversary will try their best to corrupt it in such a way that the decoding procedure gets confused. For instance, if I look at the 3x2 channel, there are 3 symbols, and when I send the first symbol, I will not get the first symbol. That's all I know, but I can get any of the other 2 symbols. So the star of our show is the Q by Q minus 1 channel. And let's try to understand what sending information across such a channel might look like. So let's say I have a codebook C consisting of M messages, which I have decorated in the rows of this matrix. So each row corresponds to a message. And the block length of this codebook is N. So we are using the channel N times. And if we think a little bit about it, it is impossible to do unique decoding for such a channel. Why? For instance, consider the message MX being sent across the channel. Okay, the corrupted word that you see on the screen is something which is a compatible corruption that happens to MX. Right, 1 can change to 4, 3 can change to 1, 2 can change to 1, and 4 can change to 3. That's something the Q by Q minus 1 channel is capable of doing. But the problem is that if you take a different message, which I am denoting by MY here, the corrupted word is also compatible with MY. You can just check, because it just requires that the symbols are different. So the decoder will have no way of knowing whether you sent MX or MY. So in such a case, we don't give up, like, okay, we can't uniquely decode, but maybe we can reduce the possible space of messages down to a small list. So this introduces the concept of list decoding, because we cannot narrow it down to one single message, which was again introduced by Elias. And it sort of it makes your code more robust in the sense that when there is a lot of noise, you don't have to give up. You can still reduce the list of possible messages to a small list, and then maybe using some side information or something, you can still find out what was sent. Okay, so the next thing we try is, okay, maybe the decoder cannot find the unique message which was sent, but maybe he can narrow the list down to a list of size 2. But you will very soon, I mean, it almost immediately follows that that's also impossible, because if you take a third message, MX, MY, and MZ, it's still possible for the decoder to stay confused between MX, MY, and MZ. Because the corrupted word that is on the screen is compatible with MX, MY, and MZ, all 3 of them. So it cannot possibly narrow the list down to 2. However, this phenomenon stops at 3. So if you take a fourth message in the fray, like mx, my, mz, and mw, the corrupted code word is no longer compatible with all 4 of them. In fact, no corrupted code word can be compatible, because if you look at the highlighted column, it has all the 4 symbols, 1, 2, 3, 4. So there is no corrupted code word which can be compatible with all 4 of them. For if it were, what would it place in the second symbol? I mean, it has to place one of these symbols, and if it places 3, then it will not be compatible with mx. If it places 2, it will not be compatible with my, and so on and so forth. So, okay, so waving my hands a little bit, it seems like it is possible to list decode with lists of size 3. And what now I'm going to show is an alternate view of what I was just talking about. If for some reason I've lost you, this is a great time to come back in, and you wouldn't lose too much for this problem. So this problem we had talked about as sending information across the q by q minus 1 channel can also be recast in this terms of perfect hash families, or in this very nice combinatorial way, where we have this set of m messages of block length n. So we decorate them in a matrix, in an m cross n matrix. And then to be able to list decode with lists of size L, what we are really saying is that if we take any L plus 1 rows of this matrix, there is one column where we see all the q symbols. So to revise, if we take L to be 3 and q to be 4, which is the setting we were looking at, what we need of our code is that for any 4 rows in this matrix, there should be one column where I see all the 4 symbols. So the highlighted column in this case has all the 4 symbols for the choice of 4 rows as shown. And what we are interested in is that, okay, for a given value of n, how large a m can we afford with this property still holding? And this presents a very elegant and classical combinatorial question, which was studied in the context of perfect hashing. So I hope the question is clear. Moving on, as we've already discussed, what we will be interested in is finding out how large can m be for a value of n, right? So a code which has this property will be called a zero error code, and the rate of such a code is log m by n, or you can just alternatively think of it as how large a m can I pack with block length n. And the best rate we can achieve will be the zero error capacity for this list size, for the list size L. Now, one thing this should be immediately clear is that if I, instead of 3, if I make L equal to 4, that means I'm asking that every 5 rows should have a symbol where should have a column where I see all the 4 symbols. So this is an easier task than the same task for L equal to 3, right? So as I increase L, the task sort of becomes simpler. Okay, with that being said, now let's try to see the literature of work that existed on this problem, and there is a lot of literature on this problem. So for q equal to 3, this is also called the preference problem. So we are talking about a 3 by 2 channel, and you want to list decode with lists of size 3. So sorry, with lists of size 2. So every 3 rows should have a column where you see all the 3 different symbols. So this problem is actually a long-standing open problem to understand its capacity, or the best rate possible, and it was mentioned by Körner as well in his Shannon lecture. The 3 by 2 problem was first studied by Elias, and he proved some upper and lower bounds on the capacity. So the achievable here denotes that there is a code which can achieve this rate, and the upper bound is no code can have rate better than the number stated. And then Körner and Martin actually improved the achievable part of it using a code concatenation technique. And then for different values of q, like q being 4 and L being 3, there was again a long line of work. Körner and Martin, Arikan, and then very recently Dalai, Guruswamy, and Radhakrishnan, where they pin this capacity of the channel more precisely, trying to close the gap between what is achievable and what is the upper bound. However, the regime which we would be interested in is slightly different from the regime we just discussed. It would be for large values of q, not for small values of q. And these two settings present different combinatorial challenges. So in context of large values of q, the most classical setting is possibly keeping L equal to Q minus 1. So you just want every Q rows in your collection to have a column where there are Q different symbols. And this was classically studied by Friedman and Komlosh in context of perfect hash families, where they essentially show that the best block length you can get in terms of M, or the largest M can be in terms of N, is governed by the equation N is exponential in Q times log M. Such a setting is achievable by random code construction, and also it is inevitable. So the lower bound is what is the shining part of this content of this work, and it was a really beautiful argument. And then Corner extended this to show that actually, even if you allow the list size to become larger by 1, that is, instead of Q minus 1, you place it to be Q, a similar phenomenon keeps holding. So of course, if you can do, if a code works with list size Q minus 1, it's certainly also working with list size Q. But the fact is that the lower bound also translates, that the exponential dependence on Q still survives. And that will be the important thing in our result, understanding this exponential dependence on Q. And then there was a work almost 20 years later by Chakrabarti, Radhakrishnan, Raghunathan, and Sasate, where they showed that if this list size Q is pushed even to a constant larger than 1 times Q, which is 1.58 Q, pretty much the exponential dependence on Q is inevitable. That is, the block length will still be some exponential in Q times log M. And one can ask, where am I going with this? But not too far. That is, if you actually keep on increasing the list size and make the problem easier and easier, something different starts happening at the threshold of Q ln Q. That is, as you shoot over Q ln Q, even by a tiny constant, the random code construction starts becoming more efficient. Instead of the block length being in exponential in Q times log M, it just becomes Q times log M. And this happens courtesy of a coupon collector phenomena, because around Q ln Q probes into a universe of size Q, you expect to collect all the coupons. And the lower bound also drops, because of course the upper bound drops. And it basically shows that it is tight. That when the list size is Q ln Q, we understand very well what the rate should be. But there is a huge gap between the two regimes, like between 1.58 Q and Q ln Q. We want to understand that when did this lower bound transition from being exponential in Q to suddenly times log M to suddenly being polynomial in Q times log M. And this is the lacuna our work fills. So we show that actually this drop happens somewhere much closer to Q ln Q rather than somewhere closer to Q. In particular, we show that as long as the list size is kept below 1/5 Q ln Q, the exponential dependence on Q for N is inevitable. So that the block length has to be some exponential in Q times log M, which depends on the gap of epsilon to 1/5. So to put it pictorially, what we knew for capacity versus Q for small list sizes was that it decays exponentially in Q when L is Q, or when L is 1.58 Q by the CRRS result. And what we also knew is that at Q ln Q, this capacity stops decaying exponentially and it only decays polynomially with Q. The question was, where does this threshold occur? And our work says that this threshold occurs much closer to Q ln Q rather than closer to Q. In particular, if your list size is below 0.2 times Q ln Q, this curve is going to keep on decaying exponentially. So in turn, it also resolves two conjectures that were raised in the paper of CRRS. And this is the formal statement in our work. It's not very important to read what this is, but essentially the gap from 1/5 needs to be some function dependent on Q, and that ends up playing a role in the exponential decay. Okay, great. So with that said, we've completed the first two results, or we've gone over the first two results that I wanted to present. Now we will move on to more algebraic battlegrounds. So the next result I'll talk about is a result on decoding multivariate multiplicity codes. This was joint work with Prahlad, Mrinal, and Madhusudan. So this all begins with a basic fact about polynomials, which we all learn at some point or the other, that if we take a univariate polynomial of degree at most d over some field f, let's say the reals for now, then it cannot have too many zeros. In particular, it can only have d zeros. So this curve can cross the x-axis only at d locations. In other words, this can be translated to distance between two polynomials. So what do I mean by that? So if you take a subset of points of a field of size n, which I'm denoting by s, and you take two distinct polynomials p and q, univariate of degree at most d, then if you count the number of places in S where they disagree, this has to be rather large. In particular, this has to be at least n minus d. Why is that? Well, if you look at P and Q and you look at P minus Q, that's a non-zero polynomial. So it can only have d zeros, but a zero of P minus Q is exactly the agreement of P and Q. So P and Q have to disagree at n minus d locations. And in other words, if I denote by delta PQ the distance, the Hamming distance between the evaluations of P and Q on S, that is the number of locations where they disagree, then fractionally this is 1 minus d over n, where the size of S is n. Okay. Now, there is a very nice generalization of the previous fact in two ways. One is by way of multiplicity. So here we are sensitive not only to the root of the polynomial P, but also to what kind of a root it is. So as you can see, the root which touches the x-axis is not only a root of the polynomial P, but is also a root of P prime, the derivative of P. So we want to actually assign it more importance, and we do this by measuring its multiplicity. So this is a root of multiplicity 2 versus a root of multiplicity 1. And we can also generalize the previous fact by talking about bivariate or trivariate, or in general m-variate polynomials. So then we take a polynomial and try to evaluate it over a grid and try to understand its zeros over the grid. Turns out that the degree mantra keeps on holding even in this generality, which is great. So in particular, if we take a k-variate polynomial P of total degree at most d, and we take some set S of size n in the field, and we try evaluating this polynomial over the grid S to the k. Since this is a k-variate polynomial, it will take as input a point which has k coordinates. So a point in S to the k, let's say. And we say that it vanishes with multiplicity m if it vanishes at a, its first order derivatives, so k of them, k first order derivatives vanish at a, its second order derivatives vanish at a, and so on so forth until all the m minus 1th order derivatives vanish at a. In such a case, we say that P has multiplicity m at a. And the degree roots mantra still says that if you take a non-zero k-variate polynomial of total degree at most d, then it cannot have too many zeros of high multiplicity. Okay? So if you count the zeros of multiplicity m, in total they can only be d by m times n to the k minus 1. So a better way to understand this is to translate it into the distance between two distinct k-variate polynomials, P and Q, just like we did for the univariate case. So it turns out that if you do that, you will get that the distance between two different, so here P is not equal to Q. The distance between two different degree d k-variate polynomials evaluated over this grid measured, where the evaluations have to now include not only the polynomial, but its first derivatives, its second order derivatives, its third order derivatives, and so on. If you just sort of play that machinery again, you will get that the distance between P and Q is n to the k times 1 minus d over mn. The way to interpret this is fractionally. Let's look at what is happening. The n to the k is really not something we should be bothered with, because that is more or less the size of s to the k. So fractionally, the distance between P and Q looks like 1 minus d over mn. And so it seems to suggest that the dimension doesn't play too much of a role in terms of the distance. And 1 by d over n is what we had already obtained when there was no multiplicity brought into the picture. The multiplicity is sort of scaling the degree by a factor of m. So instead of d, it's almost as if the effective degree is d over m. The thing to note here is that this means that as we increase the multiplicity, as we give more and more derivatives of the polynomial, the distance between P and Q increases. So we can sort of tolerate more noise, as in even if we corrupt some evaluations of P, it will be more difficult to reach Q. So the thing that we just studied in the previous slides leads to this following fundamental algorithmic question, that is, okay, you are given some subset S of F of size n, and you are given an arbitrary function from S to the K to F to the T. For once, let's just keep K equal to 1 and T equal to 1 to better understand the context. So just like a univariate function in this case, just S to F. And if I ask you how many polynomials are there, so in this case, K is 1. So how many univariate polynomials are there of degree at most D, such that the distance between P and R is small? Okay. So the distance is just the number of places where P and R disagree on S. That is small. Well, this would, how small? Yeah. So it is smaller than half the minimum distance between any two polynomials which are distinct, between any two P and Q which are distinct. You can immediately see that the answer to such a question will be 1. This is just because of triangle inequality, because if you take a receipt word R and you take any other polynomial P which is close to R, which is close, by close I mean which is less than half the minimum distance, and another polynomial Q which is also close to R, then P and Q themselves will be closer than the minimum distance between P and Q, which is absurd. And the algorithmic question then is, given this set S and the function R, can you find P efficiently? Right? Since we know combinatorially only one such P exists. So another way to think of it is, if I promise that R is actually P, that is that I have done, I mean, R perfectly agrees with P, this would just be polynomial interpolation. Here we are just interpolating, but in the presence of noise. Some of the locations have errors, and there are not too many errors. Now, of course, in this work, we want to look at a more general setting. So what we can take another setting to be is K equal to 2 and T equal to 3, where what we are thinking is that we have this polynomial P which has been evaluated over a grid. So we have a bivariate polynomial since K is 2. And at each grid point, let's say this grid location, I have given you the value of P at that grid location A. I've given you the value of its partial derivative in the X direction at A, and the value of its Y partial derivative at A. And similarly, R is also specified on the grid, as at every location I give you a 3 tuple. And in the appropriate notion of distance, P and R are close, and you want to efficiently recover P from R. So I hope the setting is clear. So of course, there is one more generalization we can still ask for, which will again relate to the notion of list decoding. So the previous question can be seen as decoding from half the minimum distance between any two polynomials, which are distinct and the maximum of total degree at most D. One can ask that, okay, what happens if I increase this half to a different constant? So I want to recover T from R, given that it is close enough to P, but not half the minimum distance, but 1 minus epsilon times the minimum distance. So you no longer have access to the combinatorial argument. So you cannot argue that there will be only one such code word, but maybe there will be only a small list of such code words, and we want to recover this list. So this is the question of list decoding. With that said, I would like to now sort of put our result in context and see what prior work we knew. So for the case of K equal to 1 and M equal to 1, this is the classical question of just decoding Reed-Solomon codes. And there were already algorithms, I think all the way in 1960s themselves, before the advent of the class P by Peterson, and then Berlekamp. May see that there was a shift register algorithm, and then there was Berlekamp Welch, and these all did unique decoding of Reed-Solomon codes. And then there was a generalization by way of multiplicity. Like we saw, there were 2 ways to generalize, where we talk about univariate polynomials, but now we talk about higher multiplicities, not only multiplicity being 1. So this was in the work of Kopati, and then later in a linear algebraic style decoding algorithm was presented by Guruswamy and Wang, where they actually not only show how to uniquely decode such algorithms, but actually how to list decode such algorithms all the way up to the distance of this code. So the other way of generalization was via dimension, where we keep the multiplicity to be 1. So we are only talking about evaluations, and we increase the dimension of the polynomial we are talking about. So bivariate, trivariate polynomials, and this leads to the classical Reed-Muller family of codes. And until recently, we actually didn't even know how to uniquely decode Reed-Muller codes when the grid S has an arbitrary structure. And then in a beautiful recent work of Kim and Koparthi, they show that you can actually uniquely decode Reed-Muller codes where the multiplicity is kept 1, but a dimension is allowed to grow. And what our work is trying to do is it's trying to sort of combine both these generalizations. So we want to look at higher variate polynomials where the multiplicity is also large. So in this work, we actually present a list decoding algorithm. That is, we not only get unique decoding, but something stronger. However, the catch is that we require large multiplicities. That is, this work doesn't work when the multiplicity is small, like 2. And we also require the underlying field to have large characteristics. There are two things that I would like to sort of say. Firstly, I mean, there are caveats here, so don't take this slide to the bank. But one note is that when the underlying grid S has a nice algebraic structure, we actually already knew how to reduce this problem of higher k to just being k equal to 1. This is using this Pelican Wu-like transformation. The second thing is in a recent work with Prahlad, Mrinal, and Aparna, we actually addressed this question when m is small, like when m is 2, 3, and so on, and k is larger than 1. So this was the sort of the missing piece in the puzzle, because this work only works when m is large. So we sort of address that regime also, trying to provide a more clear, complete picture of for multiplicity codes. Formally, this is what the result in this work states. So you fix any epsilon, and for that epsilon, there is an efficient algorithm for list decoding k-variate multiplicity codes when the distance between the received word and the polynomial that you want to decode is 1 minus epsilon times the minimum distance. And we need for this two things, as we discussed, we need the multiplicity to be large and the characteristic also to be large. And this is tight in the sense that you might wonder, okay, why can't I ask for even more robustness? What if I want this distance to be 1 plus epsilon times the minimum distance? But this is not possible, because once you ask for such, once you ask for tolerating such kind of noise, the number of candidate code words grows exponentially. So we cannot give an efficient algorithm. Okay, great. So this finishes the third result I wanted to talk about. And now we will continue a similar theme for our fourth result. This is again a result which stemmed out of trying to understand why certain codes were so good at being list decodable, and not only combinatorially but also efficiently. And this is again joint work with Prahlad, Mrinal, and Madhu. So let me dive straight into it. So again, the objects we will talk about are what we call polynomial ideal codes. So let me define them. So let's consider a bivariate polynomial EXY. By the way, how much time do I have remaining for the talk?
Prahlad, you're muted.
Yeah, so we'll go about 12 minutes so that we stop at the hour.
Okay, great.
Yeah.
So let me define what are polynomial ideal codes. So let's consider a bivariate polynomial EXY over some field F. Okay. And the bivariate polynomial has x degree S, and in fact it is monic in the highest degree of x. So the coefficient of x bar S is 1. And then let's consider some n evaluation points in the field F, A1 to AN. We are also promised that if we actually substitute for y the various values A1 to AN, the n polynomials that we obtain in just x, that is EX_A1, EX_A2, they are pairwise co-prime. In such a case, here is the code that we will be interested in. So we take a message polynomial P of degree at most k, and then for each evaluation point AI, we divide px by the univariate polynomial exai and write that remainder as its encoding. So if you notice, each of these remainders are going to have potentially degree s-1. So these are all objects which reside here. And then the entire encoding resides in this space. So such codes are what we will call polynomial ideal codes. And let's take a few examples to see how the commonly studied or popular family of codes are actually bivariate, are actually polynomial ideal codes, or can be thought of as polynomial ideal codes. So the most popular family is the family of Reed-Solomon codes, but this corresponds to just setting the bivariate ideal to be the bivariate polynomial to be x minus y. So typically you have a set of evaluation points a1 to an, and what one does is just prescribe the evaluation of the polynomial p at all these points. But that is the same as just dividing the polynomial px by x minus ai. The value of the remainder is exactly pai. So whether I give you the remainder or whether I give you the value, it's exactly the same. Now let's look at another popular family of codes called the folded Reed-Solomon codes. So these codes were very influential in the sense that they were the first examples of codes which could achieve list decoding capacity efficiently amongst them. So here the bivariate polynomial exy corresponds to this this expression. We'll get into what this expression is trying to do. So let's actually look at what the encoding of an FRS code was supposed to be. So here again, you are given an evaluation point a1, a2 up to an, and at each location, instead of just prescribing the value p of ai, you are prescribing the value at multiplicative shifts of ai. So you are prescribing p of ai, p of gamma ai, p of gamma square ai, all the way up to p gamma to the power s minus 1 ai. But if you think about it, this is exactly using the Chinese remainder theorem. This is exactly giving you the remainder of px when divided by the polynomial x minus ai, x minus gamma ai, and x minus gamma to the s minus 1 ai. And this is exactly what the bivariate ideal actually looks like when you substitute y equal to ai. So this and why are these called folded? Because, well, actually, if you think of these as distinct evaluations, like just like a Reed-Solomon family of codes, it's as if you sort of bundled a few of these evaluations into one single alphabet, and that's why they are called folded Reed-Solomon codes. And another example is an example we already encountered, which is the family of multiplicity codes. So here the ideal has a clean form. It is just x minus y to the s. So what you are supposed to do is at each evaluation point, you're supposed to prescribe the value of the polynomial. So these are univariate polynomials. Again, right now we are completely in the univariate world. So p of ai, the first derivative, p prime of ai, the second derivative, p double prime of ai, all the way up to the s minus 1 derivatives of p. However, if you just do a Taylor series expansion, you will see that this is just the same as prescribing the remainder of px when divided by x minus ai to the s, right? So the bivariate polynomial exy in this case turns out to be x minus y to the s. And then there is a lesser studied family of codes called additive FRS codes, which are cousins of these folded Reed-Solomon codes, where the shifts are not multiplicative, but rather additive. So at an evaluation point ai, I'm supposed to give you p of ai, and then also p of ai plus beta, p of ai plus 2 beta, and so on. But again, if you just use Chinese remainder theorem, it is the same as just going mod x minus ai, x minus ai minus beta, and so on, which is exactly what the bivariate ideal does when you substitute y equal to ai. So what we have seen till now is that, okay, we have a bunch of different codes which are all captured in this language. And actually, there is a generalization of all these codes which turns out to be useful, which we call the affine folded Reed-Solomon codes. So where the foldings are sort of a combination of the multiplicative and the additive folding. And in particular, the bivariate polynomial that we talk about in this setting is given by this expression x minus ljy, and the product of these as j goes from 0 to s minus 1. So what is ly? Ly is a linear form in y, alpha y plus beta, and ljy is just the composition of j linear forms applied to y. So if I talk about what is L2y, it is just alpha square y plus alpha beta plus beta, just applying L2 times. And again, the set of evaluation points is a1 to an, and we want to give the remainders mod exai. So if we just take just to say that these capture the previous examples, like if you set alpha to be gamma and beta to be 0, we get exactly the folded Reed-Solomon codes, because you can check that exy is just going to be at the location ai is just going to be, or rather in terms of y, is just going to be x minus y, x minus gamma y, so on up till x minus gamma to the s minus 1 y. If you set alpha to be 1 and beta to be 0, that is, the linear form is the identity transform, then exy is nothing but x minus y to the power s, which we saw corresponds to the multiplicity codes. So this gives you the multiplicity codes. And then the third family we saw was the additive FRS. That just corresponds to setting alpha to be 1 and beta to be some non-zero element, the shifts that you want to perform. So, at the moment, we have this rich family of codes which captures the previous codes we just saw. And what are our results in this work? Well, firstly, we show that if you take any polynomial ideal code, so not necessarily the codes that we saw in the examples, but any general polynomial ideal code, we can efficiently list decode up to the Johnson radius. Now, what is the Johnson radius? So for a code of rate r, the Johnson radius is 1 minus square root r. It represents the radius which we combinatorially, or the amount of error which we combinatorially know we can tolerate, until which the list size doesn't explode. So designing efficient algorithms up to this radius is always like a significant benchmark for list decoding algorithms. And also we show that if you specialize your attention to affine FRS codes, which are a subclass of the polynomial ideal codes, then you can actually list decode all the way up to that distance. So to put it in context, if you have rate r for the code, the distance for these codes happens to be 1 minus r, because they are MDS codes. So you can actually list decode beyond the Johnson radius for such codes, provided some conditions are met. And these conditions arise for in some cases for reasons which are deeper, and in some cases because this is more like an artifact of a proof. And the good thing about the result is that it sort of tries to put all these different results for efficient list decoding about FRS code, multiplicity codes, and additive FRS codes into one framework, and trying to understand what's really driving the efficient list decoding algorithms here. With that being said, I think I will end my talk because I'm pretty much out of time, I guess. Prahlad, am I out of time or do I have time?
Yeah, let's actually, because we...
Okay. Oh, yeah, it will be very late. Yeah.
Yeah.
Okay. So thank you guys. Yeah. And yeah, I'll be happy to take questions.
Okay. Yeah. So, any questions Siddharth will take? Else we will then move to the closed door session. Yeah.
So I have a quick question. So in the first question, the first problem on colorings, there was a point when you mentioned that, I mean, in some sense, the holy grail is to look at, to make exact sampling work with delta plus 2 colors.
Yeah, even approximate sampling. Yes.
So, I mean, like, is there a reason why delta plus 1 is just impossible? I mean, it's like, it's too much to ask for at all?
So,
or is it just because the Glauber dynamics just doesn't work?
So there are so the Glauber dynamics sort of freezes into two configurations at delta plus 1, into two different regions. There is no reason, I think, why we will not be able to get it at delta plus 1. Yeah. So I mean, I think the main point is that the Glauber dynamics we know definitely will not work at delta plus 1. There are examples, at least for some graphs, where we can see that there are two transitions, but this is not a major bottleneck because there are other locations in using Glauber dynamics where they sort of can efficiently tell you which bottleneck region to go into. Then you use Glauber dynamics. So actually delta plus 1, yeah, so delta plus 1 is not sort of clear whether we can or we can't, but I think delta plus 2 certainly, yeah.
I think it's more an artifact of the Glauber dynamics.
Yeah, this particular
I think you can do
approach
something
just
small. I think you can actually, it's not just two things. I think it can, there are examples of graphs in which it's disconnected.
Yeah, that's what I meant. You can get the Markov chain graph is not, the Markov chain is not ergodic. It has many strongly connected components.
So it should be a different, approach. Yeah. Okay. Any questions?
Yeah, I had a few questions, but I guess we'll get a chance anyway to ask as the committee, or what do you propose? I mean, I can
either way. If you think these are general questions, you can ask them now so that others can also. This one, if there's
that's what I was thinking. Yeah. So So one question, for example, following in the coloring part, do things become easier if, say, the graph is delta regular or something, or better things known?
So for the context of colorings,
Siddharth, can you also just lower your camera so that we can see you?
Yeah. So it turns out that yes, there was a line of work. It's like there is a result by Hayes and Vigoda. It's an old result and now has been superseded. But there was a result of Hayes and Vigoda where they were able to make a particular kind of argument work when they are delta regular graphs. But they had said that such results should also hold for non-delta regular graphs. It's just that one needs to work harder, but then that entire line of work got superseded. So I know that this thing certainly helps being delta regular in case of the hardcore model. I am not aware of anything for colorings at the moment which only works for delta regular. So in some cases it seems to help for spin systems which have hard constraints. So coloring is one such spin system, but the spin system where it seems to help that I know of is the hardcore model, is the independent set question. So
okay, another thing you had mentioned is that there's this LSS result which gets deterministic counting when delta is a constant. So is it obvious how to get from that to exact sampling?
So no, it's not. I mean, I think it's pretty clever. It's a reduction in the JVV paper itself, which shows if you have a deterministic approximate counting scheme, how you can turn it to an exact sampling scheme. So the crucial part here is that it's not an it's not randomized approximation, it's deterministic approximation. So the way they do it is the way you usually would do it. That is, you use some self-reducibility like property to sort of produce a sample using the deterministic approximate counts. But of course, this sample will be produced with a bias. But the point of their method is you can calculate the bias because you have this deterministic approximation schemes. And then you just do an accept reject at the very end. So that converts any deterministic approximation scheme to a perfect sampling scheme. Unfortunately, if you don't have a deterministic approximation scheme, but a randomized approximation scheme, and you follow the same strategy, at the end, the bias is not a single quantity. Sometimes you'll get something, sometimes you'll get something else. So it doesn't work.
Okay, cool. Thanks. Yeah.
Venkat, is that?
I had some more questions, but I guess it's, maybe people want to go. So I guess maybe I can ask them later too. So.
Okay. Sounds good. Okay. So then
I'm just ending the stream.